So the same thing, everything there, we're asked to graph the whole thing. So we are going to fill up the table with everything possible, and then we'll graph it. So let's get the table going. Good. Can anyone give us a domain of this function?
All real numbers except -1.
Perfect. Thank you. Good. I will plug in 0 immediately to get 1. When I set y equal to 0, x squared plus 1 over x plus 1 will never be 0 because x squared plus 1 is never 0. So there are no x-intercepts. No x-intercepts. So the only thing I need to determine are these. And then I can move on to the first derivative. So limit as x approaches infinity, let's say negative infinity from left to right, from x squared plus 1 over x plus 1. I'll say, well, it's infinity over infinity. L'Hopital's rule, wonderful. I know that. So x approaches negative infinity, 2x at the top, 1 at the bottom. When I plug it in, it's negative infinity. On the other side will be the same thing. When x approaches infinity, the answer will be infinity. Everything the same, but this time I plug in infinity, so it will be infinity. Stop me if you have questions anytime, please. Okay, so now I want these two. So limit as x approaches -1 from the left, and limit as x approaches -1 from the right, of x squared plus 1 over x plus 1, x squared plus 1 over x plus 1. The top is always positive. -1 from the left, -1.1, this is negative. -1 from the right will be -0.9. This is also positive, so positive. Done. Okay, now we continue with the first derivative. Any questions? Any questions? Okay, I don't care for anything else. Oh, x equals -1, a vertical asymptote. Very important. First derivative. Top prime 2x times the denominator minus top times the denominator prime, which is 1. So then I distribute 2x squared plus 2x minus x squared and minus 1 over x plus 1 squared. And this is x squared plus 2x minus 1 over x plus 1 squared. That's terrible. And I'm looking for my wonderful calculator to give me those solutions, those approximations already. So coefficients 1, 2, -1, solve. So I got -2.4, -2.4, and 0.4. Okay, then back to my table. Critical numbers 0.4 and -2. Oh, see what I did? Terrible. Terrible. Good. Now we have to establish the sign. Luckily, the denominator, I'm not going to waste my time on it. It's always positive. So in the numerator, when I plug in 0, I get negative. So in between is negative. If I plug in 10, it's going to be positive. If I plug in negative 10, it will be positive. Okay, perfect. Now I have to determine this point, I mean the y value here and here. Back to my calculator, the regular one. Clear. Okay, so don't forget parentheses x squared plus 1 divided by parentheses x plus 1. And then second in table, and I want negative 2.4, and I want 0.4. Okay, so I got negative 4.8, and I got 0.8. Okay. Moment of truth. See if these two work well together. If not, I'll say, okay, I put 0.4 in the wrong spot. That's why it doesn't work. So let's see. From negative infinity increasing to negative 4.8, yes, that's true. Decreasing back to negative infinity, that's correct. From infinity to 1, yes. From 1 to 0.8, yes, correct. From 0.8 to infinity, yes, correct. It appears that my two rows, the top two rows are fine, except I'm not talking about the x. So now I have to discuss the second derivative. Before I do that, I can already establish that this is a local max and this is a local min. That will already tell me the sign here and here, because if it's a local max, it has to be negative, second derivative. If it's a local min, it has to be positive. But I still have to think to see if it has inflection points. I doubt, but let's check. Because of the local max and local min. Okay, so let's look at the second derivative, which is not nice at all, because I have to differentiate this. Ugly. Okay, so the second derivative, we have the top prime is 2x plus 2 times the denominator minus the top times the denominator prime. I can factor out an x plus 1, and I will absolutely do it immediately. And this will happen in a moment later. Okay, so you have an x plus 1 times this. So 2x squared plus 2x plus 2x and plus 2. This is out, but I have to distribute 2, and it's negative 2. Negative 2x squared minus 4x and plus 2. Ah, quite nice. Ah, quite nice. As expected, no inflection points. The top is 4, the bottom is x plus 1. Never 0, no inflection points. And the sign is the one expected. To the left of negative 1 is negative, obviously. To the right of negative 1 is positive, obviously, as we expected from the get-go. This is one of the reasons why I put the second derivative last, because I may not need to look into it too much. Now, because this function has degree 2 over degree 1, it has a slant asymptote. I need to find it and graph it. Find it and graph it before I graph the function. So we have to divide the numerator by the denominator to find the quotient. So one more time, it's x squared plus 1 over x plus 1. That was our function, yes. we will be using, do you want to use long division or synthetic? Even synthetic division works here, but synthetic division has limited applicability. Would you like to do synthetic or long division? Which
What
one?
are the limitations of synthetic, if you can name them?
Yes, very good. The synthetic division is applicable only when the denominator is x minus a number. This could be x plus 5, x minus 3, x plus 10. It cannot be x squared plus 1 or any other degree. Careful, if it is 3x minus 1, you have to factor out 3 and divide only by x minus 1/3. So synthetic division is only applicable in these cases. Not this, even this, but you have to factor out the 3. So this is for synthetic. Long division, regardless of what this is, you can use it, unless it's one term. So if you have x squared plus 1 divided by x, we do not use synthetic, we do not use long. We use what we just did on the previous problem. X squared over x plus 1 over x. And this becomes x plus 1 over x. So if the denominator is just one term, there is no need for any of this. You just separate the terms and simplify. But if it has x minus a number, in this case, that number is -5. In this case, that number is 3. In this case, this number is -10. Then I can use synthetic division. And the long division works in any case. We can do both if you'd like to refresh your memory. It's up to you.
I'd say long division.
Okay, so the long division, both polynomials have to be in descending order. They are, but see, there is a missing term here, so I have to leave a space. I may use it or I may not. There is a missing term, and the missing term has degree 1. So blah, 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 x is missing. So x times what is x squared? The answer is x. But now I have to go back and distribute to both terms. X times x is x squared. I have to change the sign to the opposite sign always before I write. X times 1 is x. I change the sign. I don't have a like term. That's why I needed the space. Now these two go away. I bring down -x. I bring down +1. And I'm asking myself, the next question is, x times what is -x? At the top, I do not lie. -1 times x is -x, change the sign. -1 times 1 is -1, change the sign. And the remainder is 2. So what does this mean? It means that the function can be expressed as quotient plus remainder over the divisor. What is the quotient? X minus 1 plus. What is the remainder? 2. What is the divisor? X plus 1. Only this is the slant asymptote. Why? Because at infinity, when x approaches infinity, this is 0. So the function will approach this line at infinity. As x approaches infinity, this dictates this one is 0. So going back to my table, I have to mention in my table, so I don't forget, that y equals x minus 1 SA. Y equals x minus 1 slant asymptote. That's all I need. Do you still want to see the synthetic division or not? Okay, that's fine. So let's take a look at the graph. I don't care about any of my calculations. All I need is my table. That's it. I think I'm on page 8. When I graph a function with asymptotes, I have to graph the asymptotes first. This function has two asymptotes. It has a vertical asymptote at -1. And it has a slant asymptote y equals x minus 1. For y equals x minus 1, when x is 0, y is -1, 0, -1. When y is 0, x is 1, 1 comma 0. So 1 comma 0 and 0 comma -1. Okay, that's done. So now I look at my table. It says -2.4, -4.8. Okay, this is -2, -3, -2.4, -4.8. This was -1, -2, -3, -4, -4.8. You will have to trust me that this is -4.8. So at -2.4, -4.8. Not a problem, opening down, increasing to the maximum, coming back to -infinity. No worries there. It has to approach the asymptotes. Let me extend the vertical. It approaches asymptotically. Do not touch. Okay? Here is the local max. We don't need the calculator to determine it. We already have it. So that's done. On the other side, I have 0, 1, which is this point. 0, 1, which is that point, and 0.4, 0.8. So this is 1, 0.4, 0.8. So it's a local minimum. So we're coming from positive infinity. I don't know what's wrong with me today. 0.4, 0.8. Something is wrong with me today. Okay, fine. So here it is. Approaching asymptotically. So from positive infinity, crossing at 0, 1, the y-axis, coming to a local minimum, which is at 0.4, 0.8. This is 1, and this is 0.8. And then increasing, opening up at all times, decreasing and increasing, but opening up, going towards the slant asymptote, coming from one asymptote, coming to a minimum, going to the second asymptote, to the slant asymptote. And this is it. So x squared plus 1 divided by x plus 1. If you want to graph it with a calculator, check. That's fine. So we have to put the function in that is the slant asymptote. The calculator will not automatically graph it. Make sure you have, oh, I just erased that. Very nice. So plus 1 divided by x plus 1. And y equals x minus 1 must be a new function, x minus 1. Here it is. So I'm going to use the standard. Yes, I can use the standard. It's a good idea to use the standard for now. We can change it later. Here it is. And here's the slant asymptote and the vertical asymptote here at -1. So here's the slant asymptote and the function approaching it towards infinity. Any questions?